Hi there and welcome to Mastering V-Ray, Lesson 2, Materials 101. This video will be structured a little bit differently to the first video, as we're now beginning to deal with both technical and creative decisions. The video will be broken into two parts, theory and practical, and I'll begin by explaining some of the fundamental laws real-world materials exhibit, then show you how to implement those laws using layered V-Ray blend materials. As this video is meant to be an introduction to the material creation process, I won't be covering advanced topics yet, such as procedurals or texturing. However, you will have a solid understanding of how to create accurate metals and plastics based loosely on real-world data taken from refractiveindex.info. I owe a lot of thanks to many members on the forum over the last year, but none more so than John O'Connell. As the only person probably more interested in materials than myself, I'd like to thank you for helping me overcome a few of the hurdles I faced in understanding this material stuff and for solidifying some of the unanswered questions myself and the community has had. I'd also like to thank Peter Guthrie for providing the Sky HDR seen in this video. There'll be a link in the PDF attached to the video directing you to his new site where you can purchase some of his other HDRs. So once again, thanks to all of the people who helped me get this far. I really appreciate it, and I'm looking forward to seeing what you guys can come up with using these techniques. A couple of you have already sent me some examples, and it's looking really promising. So we'll get started with part one, and that's theory. Thanks. So when creating materials, traditionally the most important aspect to consider has always been the Fresnel value. And you'll no doubt remember going through those long lists online trying to find that correct number to plug into this Fresnel reflection slot here. The problem I found is that that simple numerical value doesn't do a good enough job of describing the way most materials reflectivity works. So the very first thing to understand when creating materials using this approach is that we won't be ticking this Fresnel reflections box. Instead, we'll be creating it with a fall-off map and a custom curve for our reflections. It can be a little bit overwhelming trying to understand what different materials' reflectivity curves look like, but thankfully it can be broken down into two separate categories, and they are metals and plastics. So before I jump into Photoshop and show you some slides and examples of what different Fresnel curves look like, I'll just show you how we're going to be creating our own custom Fresnel values. So in the reflection slot, just make a fall-off map. You can leave it at perpendicular and parallel. And if you tick the enable color map, you can see now we've got a little graph here. If you tick a little plus box, we can add our own little point. And here we can begin to create a fall-off curve on the reflection. If I bring this example up, you can see now as I raise or lower it, the reflectivity changes. So an interesting thing to notice is that you can reproduce the default value of 1.6 just by going in here and bring this up just a little bit. Sorry, we've just got to untick the Fresnel. So you can see that changing that value more or less reproduces exactly what's happening with the default Fresnel value. If I change that to 3, go back into this material, all I've got to do is just kind of raise it up a little bit. And you can see it matched. So I'll just stop there and show you what actual values look like. So what you're looking at here is two different Fresnel curve examples that I've taken from the Cornell University website. On the left you can see a generic metal Fresnel curve, so something like typical aluminium, and on the right you can see a generic plastic Fresnel curve. Now the actual values you see in these graphs aren't as important as showing the difference in reflectivity between these two materials. As you can see, the generic metal material maintains a very high reflectivity regardless of the viewing angle. However, the plastic material behaves quite differently. You can see here as the viewing angle increases, the reflectivity starts to ramp up, but not until about 40 or 50 degrees. For those who don't understand what these graphs are showing you, it's quite simple. All you're seeing is the material's reflectivity in relation to the angle in which you are viewing it. So on the right here we've got the angle from normal, and vertically we've got the reflectance. So let's take a look at this effect in real life. So what you're seeing here is an approach I developed while I was at Electric Art when I was trying to understand how materials behaved based on the viewing angle. So basically what I did was I opened up a high contrast texture on my iPad or iPhone and placed it directly behind the object or material I was viewing, and observed what was happening as I saw it closer and closer to the grazing angle. Now, it's definitely a rudimentary approach and by no means scientifically accurate. However, it does do a good job of showing the Fresnel effect, as well as another more important feature of complex materials I will get into in just a minute. So let's start viewing it from different angles and see what happens. You should go back and replay this part a few times, but ultimately you can see as you view the Wacom surface at different angles, the reflectivity changes also, and it changes in a way that very closely resembles the plastic Fresnel curve we saw in the earlier graph. So now that you understand that reflectivity changes based on viewing angle, you need to observe how reflection glossiness changes based on viewing angle also. This second material feature is ultimately the reason you bought into Mastering V-Ray, as it's been a very hard and costly effect to reproduce in any 3D package. Thankfully, this video is going to break it down for you, but before I do that, let's take another look and I'll point out the effect to you. So in this first slide, you can see the reflection's extremely matte. There's no mirror quality finish to the material. You can't read anything in the Mastering V-Ray. In the second slide, it's still pretty much the same. Extremely matte reflections, no visible detail in the circle or the Mastering V-Ray text. In the third slide, we can finally start to see that the glossiness of the material starts to get a bit higher towards, maybe like 0.8 in V-Ray. At extremely grazing angles, we can see that there's visible mirror-like finishing, and there's like checker detail. You can see the Mastering V-Ray. And finally, in the third slide, where we're almost at 90 degrees, I had to basically be underneath the table to see it from this angle. We can see that there's a very high mirror finish quality, but at the same time, it's still a little bit glossy. So it's this important feature in materials that we're going to create now, and ultimately what's going to make your materials look a lot more realistic. So as you know, the bidirectional reflectance distribution function describes a material's glossiness, but what you might not know is that there are two different kinds of BRDFs currently being written: simple and complex. Unfortunately, at the moment, V-Ray only has simple BRDFs, and as you can see, it means they aren't capable of producing multiple specular lobes. To simplify things for the average user, what it means is that the glossiness spreads uniformly regardless of viewing angle. However, what we just observed on the Wacom surface paints a very different picture of what's actually happening. This next image shows you the difference between a complex BRDF and a simple BRDF. On the left and right, you've got V-Ray's standard BRDFs. You've got Blinn and Ward. And in the center, you've got the custom one we're going to be creating next. And you can see that there's a non-uniform glossiness distribution as opposed to the Ward and Blinn, which is just the same throughout. So it's this center effect that we're trying to produce. So let's go back into Max now and get on creating it. Now that you understand the basic theory behind complex materials, I'll begin by showing you how to create a simple layered plastic material. As I've created so many now, I don't often need the real-world data to determine a material's reflectivity. I mean, it becomes a pretty repetitive process eventually. However, during this initial learning phase, I've got to go through everything for you. So it's always good to know you're sticking to actual physical values. The best place to obtain that information is at refractiveindex.info. So if I just go there now, you can see what the page looks like. Now there's a couple of important pieces of information I will describe when we advance to making colored metals, but for now I'll get you to swap to plastics in the drop-down menu. Change the material to polycarbonate and set the wavelength value to 0.55. Now that number is an average of the red, green and blue wavelength numbers that make up most complex metals and stuff like that, but for now that value of 0.55 is good enough to represent simple materials that don't change color based on the reflection angle. So for plastics, this is all you need to worry about, as they aren't complicated. Alright, so once you put that in, scroll down the bottom here and you'll see that there's a reflection calculator section. Now this graph here has all the information you need to reproduce the Fresnel curve of this polycarbonate material. So looking at that, one of the things you can do here is you can save out a JPEG of that. So if you just click here, save a JPEG, you don't need to go back to the website, so while you're in Max you can just have that image there. You can see it produces this graph here. So if we go back into Max, this is the graph that we're going to try and reproduce in the reflection slot, and we've got all the information here to do that. So like I said earlier, we're just trying to reproduce the green line here. Now it might be a little bit confusing to see this S polarized and P polarized and non-polarized line. Basically the green line is an average of the red and blue lines. They're just different methods of capturing the reflectivity of a material, and neither are perfectly accurate, so they just average the two, and all you need to focus on is this green gradient. I was a little bit confused originally. I thought it was the red, green and blue wavelengths, but it's not. It's just all you need to worry about on that site is the green curve. So in here, let's go back to that original plastic we were creating. Fresnel's been unticked, and in the reflection slot, you can see we've got a very wrong reflection curve here. So go back into this JPEG image, and we can see at 40 degrees the curve is still pretty much flat. So we know here, if we go in this slot, if we set it to 0.4 here, we need to level that out. And if we look at the reflection map again, at 70 degrees, we're at 0.2 reflectivity. And you just do your best to match that gradient. Another bit of important information you need to match is the initial starting reflectivity, and you can see it's about 0.06 or something like that. So just go in here and input that. So there you go, there's the reflectivity of a polycarbonate plastic. Now that we've matched the reflection curve, we need to go in and create a layered material to reproduce the glossiness based on the reflection angle. It's best to just render off what we've got so far. Before I do that, I'm just going to swap to a more yellow material. It just makes it easier to visualize the reflection. So just set it to 25 and 255, 255. I'm just going to render that. Every time I do a test render, I'm just going to pause the recording just to make things a lot quicker. So if it skips, you'll know why. So now that that's rendered, the next step is to make this into a V-Ray blend material. So click here, make it a V-Ray blend material, and keep the old material as a sub-material. And now you've got your base in the base material slot. We're going to duplicate that into the coat material slot. So drag that over, make it a copy, just change it to plastic coat 1, any naming convention that you're used to. And now we've got two layers. You can see the value, the reflection glossiness value in this base material is 0.6. Now we want to get, as we get towards the 90-degree angle, we want that glossiness to go up. So I'm going to make this 0.8. You can see that changes the material preview. But we need to blend based on the viewing angle. So what I'm going to do is I'm going to copy that reflection map and paste it into the blend amount. Now we want this to blend kind of 50% with the original base coat. So this curve is going to look different to the reflection fall off curve. Unfortunately, there's no real world data, or there's no website like Refractive Index that will give you that glossiness value. So we kind of just need to eyeball it. So for this initial video, just using some rough values here, and if you slide that up to 0.5, you can see now that we're blending the glossiness based on the angle. So it's going to be more matte on the facing angle, and as we get towards the edge, it's going to be more glossy. The problem with only using two layers in the material is that you don't often get a very nice gradual transition between a matte material and a highly mirror finished material. The problem is I don't like the slow render times of using three materials in a blend, but sometimes you've got no choice. For plastic, you can probably get away with just two layers, but to demonstrate the realistic approach to this, we're going to go in and make another layer, and that last third layer is going to be the mirror finish layer. So drag it over again, and now from 0.8 we want to change that glossiness to 0.99, and you can see it's producing a mirror finish. Just rename it. Just got to rename the base. And we can copy that glossiness blend amount curve. And we only want this top coat. You'll notice if you look at the Wacom surface again, you'll notice that mirror finish is only appearing at very, very grazing angles. So we need to blend this representing that. So go down to 0, slide this curve in a little bit, and then drag it out. So what this new blend amount is telling us is it's only going to use that mirror finish material on these far grazing angles. So now we go from 0.99 glossiness down to 0.6 based on the blend. So I'm just going to do another render of that and show you the difference. I'm just going to save this initial render in the history. And I'll re-render. Just going to set this new one as A and B so we can compare the two. Now if I slide between them, you can see that subtle effect that's happening. The problem is the render time's gone up an extra 30 seconds, and that's always going to be the trade-off between low quality and high realism. Just zoom in here. So it's a subtle effect, but it's also a realistic effect, and it's something I think you kind of need in all of your materials. Once you've got the structure of the material set up, it's pretty easy to change things. So we know that the reflection amount's not going to change now, so that's going to stay the same throughout. So you can go into here, you can copy that reflection curve, and you can just paste that as an instance. You'll notice I work in the old school material editor. I don't use Slate. Feel free to use Slate if you want, it doesn't really matter. Alright, so that top coat, just before moving on to metals, just going to tweak a couple of values just to get it looking a little better. It's probably not blended enough, so we want to slide this back a little bit and just set it to be a little bit higher than 0. If I ramp this all the way up, you'll see what happens in the material preview. We're getting more of that mirror finish and less of the matte finish. Just going to re-render again. So the difference is too subtle to realize in this plastic material. It's just not reflective enough to demonstrate that blooming highlight effect. So naturally the progression is to move on to creating metallic materials. So I'm just going to stop the video here and start up again, and we're going to create a metallic material using the same exact process, just using slightly different refractive index information, and I'm going to try and really highlight that effect of a blooming highlight. Just quickly before jumping into making a metallic material, I'm just going to drop back that slide in that you saw in the theory section just to reiterate what I was describing earlier. So now we've created the plastic material. You can see this blue curve, and now we're going to go in and create a metallic material. When you open up this starting scene, you'll see that there's already a couple of materials created for you. One of them is a gold material and the other is a silver material. They weren't designed to look like any real world material, but more so to show you how they're structured. So if we go into the silver material, you see that it's very similar to it's basically identical to the plastic. You've got a base coat, you've got two coat materials, and blends for each of those. Now the gold's identical again, except there's one key important difference when you're creating colored metals, and that's that the RGB component is split out. So if I go into the reflection amount here, you can see that there's a red, green and blue component. So I need to explain that to you. Now all metals do have a red, green and blue component. They're just very similar usually, like silver for example, so you can't see that colored tint in the reflection. But just the same way that you can blend the reflection amount based on the angle, you can also blend the color based on the angle. So where am I getting that information from? Well, we need to go back into the refractive index website. We need to change it to metals. And let's just go into aluminium. Now here's where we need to look a little bit more closely. And we need to understand what the red, green and blue wavelengths mean. So what I've done is I've done a Google search for red, green and blue, and on the Wikipedia page you can see the value in nanometers of the wavelength for each spectrum. So the red wavelength is somewhere between 0.6 and 0.74 micrometers. If we go back to the refractive index website, this little symbol that looks like a U is just in maths, it's just short for micro. So it's just saying the wavelength in micrometers. So if you go back to red, you can see it's going to be somewhere between 0.6 and 0.7 for micrometers. So let's just put a value of like 0.68. If you put that value in and reload it, you'll see here that we're getting a value, a graph that looks very similar to that metallic example I showed you just before. Now we need to, that's what we're seeing now is only the red wavelength. Like I explained, each material is made up of red, green, and blue wavelength. So we need to separate those and see what each looks like. So if we go into the green wavelength, we can see it's got a value between 0.52 and 0.57 micrometers. So if we put in a value of like 0.54, we can see the green wavelength. And it looks very similar to the red. So like I explained, with silver materials and metals that are more grey, that red, green and blue wavelength is going to be very similar. That's not the case for coloured metals like gold. So if we go into gold and put that value of like 0.68 in again, we take a look. Now you'll notice gold's predominantly a red material, so as you'd expect, the red wavelength is highly reflective. So I'm just going to download a JPEG of that. Takes a little while. Now we're going to go in and put the value for the green in. Let's go 0.54. Reload that. Now there's less green showing because more red is absorbed. Just going to download that one. Okay. So you can see here we've got the red wavelength, we've got the green wavelength, and lastly is just the blue wavelength. So we go into the blue wiki page and we can see it's between 0.45 and 0.49 micrometers. So we'll just put a value of 0.47 in, just averaging that. And the blue wavelength is once again even less. So just download that. So there you go, we've got the 3 different wavelengths for gold. Now we can go into Max and reproduce that. So once again, just going to create a base material. For now, metals do have a subtle diffuse value, usually with a kind of grime texture, just because of impurities in the metal. I'm fairly certain though that 100% pure metals don't have any diffuse component. So in the reflection slot, we're going to use the same process as we did before. Going to create a fall-off material, keep it perpendicular and parallel, and this time instead of using mono mode, we're going to use RGB mode. It's pretty funny. This is where I have to kind of thank John O'Connell, because when I was trying to come up with this process, we were actually blending 3 different materials with different red, green and blue components. So what we do is we'd make a reflection map, set this to green, and when you blend all 3 in a blend material, you end up with a white reflection. It was kind of labor intensive, so this way sorts that out. So if we go into the red channel, we can see that it's pretty much fully reflective the whole way out. So I'm just going to untick the green and blue channels, add a point here, and just slide it well and truly up. Make it a smooth Bezier handle. So there's the red component. If we untick the red component and go into the green component and check out that curve, we can see the starting reflection is just above 0.8. So we can slide this channel up, like 0.805 or something. Add another point in the center. Just double check again. And at about 60 to 70 degrees is when it starts blending. Now don't get confused, because in Max, this value on the right, which is the normal angle, goes from 0 to 1. In these graphs, it's going from 0 to 90 degrees, so it's not going to be identical. You're always going to have to push it a little bit further. So if it's starting to become reflective, more reflective at 60 or 70 degrees, we need to move this a little bit further. Now what you'll notice is we're starting to see some color in this reflection map. If I tick on the material preview, there you go, you can see that appearing throughout. Now lastly, we just need to go into the blue channel, and it starts out at about 0.4. So untick the green and tick the blue, and slide this up to about 0.4. Same process, add another point in the center, and it starts becoming a bit more, the blue wavelength starts becoming a bit more reflective from 50 to 60. So you can go about 0.55, something like that. And there you go. We've just entered in, if I re-enable the red, green and blue, you can see the three different channels creating that yellow tint seen in gold. Now don't take it too literally, because on the Refractive Index website, this was sampled on, this is giving you a pure scientific value for that metal. It might not exactly look like that in reality. So always base these values loosely. And if it doesn't look right, it doesn't look right. If you need more gold, or if you need more yellow in your material, go into the green and blue. And if you drop them down, you'll get more of that gold reflection color. So just eyeball it, do it to what you think looks right, but you will need to separate the red, green and blue to create those colored reflections. We're very close to finishing up this first video, but we'll just finish off creating this gold, and I'm going to create the exact same process, just go up to 128 on the reflection. Now one difference between plastics and metals is we need to use a different V-Ray BRDF. It's not ideal at the moment. Ultimately, what I'd like to see implemented is a GGX BRDF, and I was saying earlier how there's simple and complex BRDFs. What the GGX BRDF does is it does all this work for us. It simulates those multiple layers and the blending of glossiness based on the angle. So it's a lot more complex, but for now, with metals, Ward works a lot better than Blinn, and for plastics, Blinn works a little bit better. So always tick Fix Dark Glossy Edges, and in the options slot, make this 0.01, just so the reflection isn't getting cut off. So we've set it to Ward, and now we can make this base layer whatever you want, but I'm going to make it the same as what we did on the plastic, and set that to 0.6. And you can see we've got an extremely glossy metal. Actually, instead of 0.6, I'll go 0.8, just because it's extremely blurry. And I'm just going to tweak a couple of those reflection values just so we've got a material that's a little bit less reflective. Alright, I'm just going to assign that to the shader ball and render it so you can see where we're at. So there you go, you've got a material that does look like gold, but in the exact same way as the plastic. We've only got that fall off effect on the reflection, and we don't have the glossiness blending. So I'm just going to recreate exactly what's happening in the plastic, but with these metallic values. So create a blend material again, keep it as old, just call this gold base, doesn't really matter, whatever naming convention you want. Just going to drag it in, gold, code 1. So the first coat material, we're going to go up to 0.9, and the second we'll go 0.99. Copy the reflection, make it an instance. I'm going to copy the reflection and paste it into here. Now, the difference is I've pasted that reflection in to the blend and it's got color in it. So that's not what we want. So the easiest thing to do is just to steal the reflection maps from the plastic and paste those in. So if we look at the quick material preview, we can see now that we're getting a blended specular highlight. It's going from glossy to very sharp, and near the edges it's becoming more of a mirror finish. So I'm just going to save this render and re-render with this new blended material applied. So I'm just going to compare those two now. And if I slide between them, the effect is a lot more noticeable this time, and we're getting a lot better result. So if you zoom in the details here, before the reflections appear very flat, now we're picking up a lot of extra detail that wasn't there before. So basically, to summarize, that's how I've been creating these materials for the last couple of months. The materials I released in that initial pack varied all over the shop because what you were seeing was a slow progression of the old method I used and the new methods, and it results in sometimes a bit of a messy material structure. So any materials you create from this point on should be roughly based on this idea of blending, setting the reflection amount correctly and then setting the glossiness correctly. You can of course use maps in any of these slots for the glossiness. For now though, I've kept it kind of very simple and very easy to understand so you can get your head around this material creation process. In the next video, we're going to go back into optimizing V-Ray and a more complex scene, and I will jump into a scene that was released by Peter Guthrie, so you can look forward to that. I just want to apologize for this video being so late. A lot of things came up that I didn't expect, but I'm back on track now. So thanks for your patience, and I look forward to releasing the next video very soon. Thanks heaps.